All right. Hi, everybody. Seems loud today. Yeah, welcome back from spring break. I hope that you were able to take some time off. We are going to be continuing on with, is something wrong with the microphone? It sounds very echoey in here. Up. A little bit better, but similar. It's okay. I can deal with it. I can just hear myself coming back. So we have passed spring break. So we have maybe 40% of the course content left. And we are on the precipice of exam 2. And we have homework assignment 4 out to you. And so, yeah, this should be up shortly here as it syncs everything. But I wanted to just give us sort of a status update of where we are in the class, what we've covered so far, and then what you might expect on the exam, okay? So there was a really nice example problem on problem set 3. And you know the one I'm talking about. It's the first one where it had the big mass and it was mounted on the 3 spring clips. And then it was thrown in the back of a truck and driven across the country. And come on now, guys, what are we doing? Those spring clips, we had to analyze if they would fail due to fatigue. And so it took going all the way back, for those of you that sort of solved out every part of the problem, going back to mechanics of materials, right? How do we determine what the stresses are in a particular part of a compound beam component? And then what is the stress state, which we talked about at the beginning of the semester? What are the principal stresses? Does it fail due to static loading, right? And so we had some complicated examples, but the concepts of those things were things that you should already have a lot of experience with. Then we moved on to talking about multi-axial stresses, failure theories. Here, let me pull this up. So here's the example problem. Right. Okay, perfect. So that's just the schematic of it. And so that was the kind of the first thing you should check on this. Is it going to fail if we just load the mass on and leave it there, right? And so there should have been a fairly high safety factor to yielding. And the safety factor that you found, from what I saw when I was looking through all the assignments, is whether or not you considered the 3,000-pound mass to be distributed equally among all of those clips, or whether you didn't consider that part. So if you distributed the 3,000-pound mass equally among all 3, then each clip had 1,000 pounds pulling down on it. And so you should have gotten a fairly high factor of safety on the static yielding. And then the problem told us that this component was made to be flexible, right, as it's bouncing around in the back of a truck. And so it had an amplitude that was the amplitude of the oscillations, right, up and down, so that would be 2 times the amplitude, was approximately equal to the magnitude of the deflection or the stress as it was sitting stationary, right? So we have a non-zero mean stress, we have fluctuating stresses, and so you got to put into practice not only basic fatigue knowledge, but also non-zero mean stresses. And then it also told us that there was a loading spectrum, right? That it was full scale for some portion of the journey, and then it was 3/4 of that for some portion, and then half of that amplitude for some portion of the journey, right? And so if the stresses were high enough to use a cumulative damage theory, then you could have pulled that out of your toolbox and used that as well. So that's what we covered before we sort of got to this problem. And then we went back to chapter 3, and we talked about fracture mechanics. So when we started talking about the mechanics of fracture, and specifically initiating a crack and propagating a crack, Then we left behind sort of the conceptual ideas of there may be a crack, there may not be a crack, or you're just compounding the damage. And so that is part of what's going to be on the second exam. Let me see if I can go forward here. Okay, so what concepts may appear on exam 2? So cumulative damage, that is maybe past the Palmgren Minor kind of linear damage rule, right? We had some other theories. We had the double linear damage, and then we had the, I think it's the Henry theory, where we had a fatigue-affected endurance limit that kept dropping and dropping. And the reason that we need, I guess, multiple cumulative damage theories is not so that we can apply sort of a very even known spectrum, but rather if we have more random stresses, or we have just fluctuating stresses that don't follow a pattern that we can readily apply. So if we can identify kind of the character of stress fluctuations and implement a counting method like the rain flow method, then we can implement something like a cumulative damage theory. And then in chapter 8, there was a lot of assembly of ideas, right? So chapter 8 was kind of a mishmash of ideas, and there was example problems in the middle, example problems at the end. But what chapter 8 tried to help us do was put together fatigue, what we know about fatigue, and what we always use, which is that SNP diagram, right, with multi-axial stress states, right, that may have kind of random fluctuations, right, or a stress spectrum that's not easily captured by a pattern. And so if you are able to complete the problem sets that include problems from chapter 8, then I think you will be well prepared for the exam. So that would be problem set 3 and problem set 4. I'm planning to post the answers to those with some kind of logic along with that, not just a sort of a numerical answer, if I can after class today. All of the grades for exam 1, problem set 1 and 2 have been released. And so that's kind of what I wanted to just talk about here at the beginning of class. For those of you in person, do you have any questions? Do you want me to clarify anything about kind of where we are in the course, what we're looking at this week? No? Okay, so we're all in the same spot. All right, good. I wanted to use today to bring the concepts that we've been learning a little bit back down to earth, right? So we're in class and we're drawing stress spectra and we're drawing plots and we're doing a bunch of math and deriving equations, looking at failure envelopes and things. But I wanted to tell you a little bit about how these are then used, right? And how they were developed and used in the real world. So you all are highly trained, highly educated folks who may one day have the chance to be in charge of projects that are either using new materials that haven't been characterized before, or checking the data for known materials such that you can choose appropriate materials for something that you're designing. Or if you choose to pursue the path of becoming a professional engineer, where you take the tests and do the sort of apprenticeship under a professional engineer, then you might be the one who's, like putting your stamp on these drawings and these plans such that they can go into production and things like that. And so the way that, that engineers decide how to use materials and if they're sufficient and up to a task is by doing materials testing. And so we've been looking at a lot of plots, and I have talked a little bit about statistics in the class so far when we have like an SN diagram. I'll show another one today. There is an entire chapter of the book dedicated to statistics. It's chapter 9, but it really does not introduce anything new beyond sort of a basic statistics course. So we're not going to cover chapter 9. and I'm only going to refer to things that most people have a very good understanding of, right? The mean of a distribution, the standard deviation, and some reliability type numbers, right? If I made 100 measurements and I had a specific distribution and I made one more measurement, where would I expect it to fall based on the distribution and things like that? And so these standards that were developed for fatigue testing take into consideration these statistics. That's why it's covered in the textbook, right? You could consider our textbook to be a logical collection of journal papers and reports and standards like these that have been developed through a lot of empirical testing, and very large committees of people have sat down and said, if we do it this way, it will be standardized, right? And so that's why I wanted to present this to you, so that you would have an idea of what is the scope of these type of standards, what is the level of detail of things that are specified, and then also maybe what things are left out. So when you are looking at this kind of data, you're asking a fellow engineer, how did you collect this data? Did you follow ASTM E466, right? Things like that you can check up on that and know that that was done correctly. I'm going to present 3 ASTM standards briefly today in class. I'm not going to read through every word of them because they're all kind of 7 to 15 pages. But these are sort of the very most common ones that are used for fatigue testing. So this one is E466, and it's called Standard Practice for Conducting Force-Controlled Constant Amplitude Axial Fatigue Tests of Metallic Materials. Okay? So this gives you an idea of what kind of materials it applies to, metallic ones. It does not say ferrous, non-ferrous. It doesn't break down the type of metallic materials. So if you have a material that could be considered metallic, but maybe also not, then you may consider using this one, or you may have to find another one, right? Especially if you're doing something with semiconductors, polymer composites, other types of materials. Some of the things may be similar between those standards, but they may be very different based on the strains, the higher strains you might expect, and the different types of deformation mechanisms. We can see that this is about conducting the tests, right? So I'm just going to circle that word, conducting. And it says force-controlled constant amplitude axial fatigue tests, right? So this is not multi-axial. This is just single axis, right? And it's force-controlled. So we're going to be stressing a common specimen or a series of identical specimens to force-controlled levels, right? So we have to have force feedback on the load frame, right, in order to pull it up to some level of force and then release that force. And in this case, it's releasing the force back down to 0. I'll tell you how I know that in a little bit. That's the example that they give anyway. I believe that you could have fully reversing tests that fall under this standard as well. Okay, so we've covered sort of what the title tells us as far as the scope. Okay, this is about sort of the procedure, right, and how to do the test. And so it starts with specimen preparation. And if you've taken any kind of class where you got to see a tensile test, and you'd be very familiar with these kinds of things. So in this standard, it does not say that it's conducting these tests with only one type of geometry, or with one vendor of load frame, or with one particular stress level, or anything like that. So it recognizes that you could use many different types of equipment for this. So it does not specify the exact equipment, other than to say you have to be able to load the sample and align it and have force feedback and things like that. So here it says that you have to have a sample that generally follows these type of guidelines. This is one example. So this one is a specimen that is cylindrical and it has tangential blending of the fillets between the middle test section and the end, which means there's a constant diameter section in the middle, and then there's a prescribed radius out to the non-test area of the specimen that's going to be mounted in the chucks or whatever. And all it has to do is sort of generally follow this geometry. It doesn't have to be a specific size, but they do give a preferred size. So they say the diameter should be between 0.2 inches, right? So that's pretty small, right? Less than 1/4 of an inch, 5 millimeters, and 1 inch. Okay, so you have to have these specimens sort of handheld type size, but they can vary in diameter by a factor of 5. And it says to ensure test section failure, the grip area should be at least 1.5 times, but preferably at least 4 times, the test section area. Okay, so that means you have your area in the middle, that's your test section, and that's where you expect it to fail. And then you have the ends where you don't expect it to fail. And it says the area of those should be very large, 4 times or at least 1.5 times. And it says it gives guidance as to the blending fillet radius, at least 8 times the test section diameter, to minimize the theoretical stress concentration factor, KT. Because we know from our prior classes and things that when we have a discontinuity in a sample like this, that is what gives rise to stress concentration factors. So we want to basically have a smooth change in dimension to minimize that stress concentration factor. It tells you how long the sample should be, 2 to 3 times the test section diameter. Okay. And then it gives a special caveat for tests run in compression. The length of the test section should be 2 times the test section diameter to minimize buckling. So if we make these test specimens really, really long, and then we put a compressive load, they're now susceptible to buckling. But if we're doing axial tests, the length, it's less sensitive to that length. So this is just for this particular type of geometry here, and it gives similar specifications for if you want to have a continuous radius, right? Maybe you don't want to say it's going to fail anywhere between here and here. You say it's going to fail right here at the center, so I'm going to have a continuous radius with a minimum diameter where I expect it to fail. And so it gives specific geometrical relationships there. There's some very strong language in here when talking about specimen preparation and specimen mounting. So it says the condition of the test specimen and the method of preparation are of utmost importance. Okay, so this language is kind of where we're reaching the limits of what the guidance is that they can provide, right? Because they're trying to present a standardized way of doing everything, but there's no governing body where you send a photo of all your specimens in and then they approve and then you go ahead and do the testing. This is an agreement between the testing lab and the customer to do this correctly. So this is where we get into just people trying to do due diligence and having integrity in what they're doing. It says improper methods of preparation can greatly bias the test results, and that can be very bad because if we get the wrong endurance limit and we base a design off of that, then we could be wrong in how long a part will last. So really, it says in view of this fact, the method of preparation should be agreed upon prior to the beginning of the test by both the originator and the user of the fatigue data to be generated. And so this speaks to sort of the larger world of engineering, where it's not just us saying, here's the data, do what you will with it, but rather, before we even work together, here's what we're going to agree on. A procedure of specimen preparation that we can both agree on. Okay, and then I'll show you an example of a preparation procedure. But it says, I'm just pointing out sort of the most important parts of what's in this specification. It says once a technique has been established and approved, and test specimen configuration, et cetera, change should not be made because of potential bias that may be introduced by the changed technique. So once you get a set of samples and you say how you're going to prepare them all, you got to do them all that way. You can't change midstream. This entire procedure should be clearly explained, blah, blah, blah. Okay. At the end of I know this text is really small for reading in the classroom. At the end of the ASTM standard, it provides an example of how one might describe the sample preparation procedure, and I'll just tell you the different stages of it. So first, it says that you have to machine it to the particular dimensions that you decide. And then it tells you in the final stages of machining, remove material in small amounts until some amount of excess material remains, right? So we're going to machine the whole thing down until we leave a little bit bigger than we want our final dimensions to be. And it tells you how much to leave on there. And it says, okay, then remove that layer that was retained by grinding, right? Cylindrical grinding. And it gives you a rate to follow, right? So this would be a finishing procedure. So it's not a one-step machining, right? So you can use whatever you want to machine the sample. You can use a lathe, CNC mill, whatever, but you have to leave a little bit of material on there, and then you grind that off to leave a smooth surface. And it tells you, remove the final thousandth of an inch, or quarter of a tenth of a millimeter, by polishing longitudinally to impart a maximum surface roughness of, then they give a number there, in the longitudinal direction, okay? And I'll come back to that in a moment. But it even tells you how, like an example way of, here's how we finished the machining. So there are actually one machining step and two finishing steps in order to prepare the surface of this sample. And they even give a roughness spec, right? So you could take like some kind of roughness measurement device, do a quick line scan, get a roughness, and make sure that it is 0.2 microns or 8 micro inches, right? And it says to take extreme caution, not just normal caution, extreme caution should be exercised in polishing to ensure that you're removing material rather than taking a very, let's say, ductile material and just smearing it all over the surface, okay? It says all grinding and polishing marks should be longitudinal. No circumferential machining should be evident when viewed at a 20x magnification under a light microscope. Degrease, if heat treatment is necessary, do a heat treatment, and then write down any observations that you have. Imprint specimen numbers on both ends of the test, away from the grip contact surfaces, right? So this, if you read these kind of things, it's not only going to help you become a better engineer for sort of supervising if people are following procedures, but also if you're doing research, right? So this is helpful for anyone who makes specimens, right? So you want to make sure that they are how you want them, and at the end, it even says here, label them, right? So labeling, very important. And don't label it in such a way as it's going to be damaged. Like it says, imprint the specimen away from grip contact. So if you put it in a grip or a chuck, you don't want to label it underneath that, right? So it's not everyone is a highly trained, highly educated engineer like yourselves, and so they need that level of care, right? So then comes the testing procedure. It says that you want to apply maximum and minimum force from the desired values, and it should not exceed 2% of the desired amplitude, right? So if you decide X number of X thousands of pounds, and then it goes, 5–10% above that, then according to this, it's really doesn't meet the specs of this standard, okay? And they're not saying this, they didn't come up with this 2% of just like, I don't know, let's just throw it out there, 2%, right? This feeds back into these statistics. All right. So someone either within ASTM or over at the NIST, National Institute for Standards and Testing, has done the math on if you have a variability or you exceed X% in your target loads, it's going to affect the reliability of the result, maybe in such a way as to be not as confident here. So these numbers all come from somewhere. And then they give a test frequency, right? You might say, well, I just want to get this fatigue testing done really quick. Let's accelerate it. Let's do it at like 2 kilohertz, right? So they're going to come in and say, like, no, you can't accelerate the fatigue testing in that way. You can only do it between 0.01 and 100 hertz, right? And that's because you want the material behavior to be in a regime where it stays the same. So it says that so fatigue strength is generally unaffected at those frequencies. But if you go into other materials systems, or you have too high and you generate a bunch of heat, right? You can get localized yielding, you can get strain rate effects, or if you go too slow, you could get creep. So you really want to be in this moderate range of frequencies where you're not too fast and you're not too slow. And so it provides guidelines for these kind of things. And it says here under procedure, mounting the specimen, right? So literally, this is the person that has your specimen or has their own specimen, and they're walking over and they're literally tightening it, into the load frame. It says, by far the most important consideration for specimen grips is that they can be brought into good alignment consistently from specimen to specimen. And the reason for that is because we want pure axial loading, right? If we have off-axis loading or something like that, it's actually going to cause maybe some added shear this way or some bending or something like that in the sample, which we do not want. It says every effort should be made to prevent the occurrence of misalignment, either due to twist or to displacement in axes of symmetry. And then there are some ways to kind of check the alignment, right? So this is important, and these sort of really important things are often done by someone without an engineering degree, right? So that's why we have to specify and check up on these things. How do we know when the test is over? Well, for these types of tests, we define that, or the test lab and the customer will define that, okay? It says continue the test until the specimen failure criterion is attained or until a predetermined number of cycles has been applied and there is no failure, right? And it says failure may be defined as complete separation, a visible crack at a specified magnification, as a crack of certain dimensions, right, once we reach a ½ inch or whatever, or by some other criterion. In reporting the results, state the criterion selected for defining failure and be consistent with any given data set. And so this is really often the problem with doing research or working in a field where there's sparse data, because you may get 3 or 4 reports, right? Let's say you're working with a new alloy and you think it's like very, very durable and has a lot of ductility, is very resistant to fatigue failure, and you get various reports, right? You hire 2 different labs because you want to make sure the testing is done right. And then you get back one and you've defined the failure criterion as, a visible crack up to a ½ inch through the thickness. And the other one, they sort of missed that email and they define failure as complete separation. Well, now you have 2 different failure criterion for the same type of samples, and you have to interpolate between those 2 and decide what you want to do, right? So it's really important to communicate at the beginning and make sure that everyone's clear on the terms. And then finally, what do we report out according to this standard? That would be helpful. So it says, report the following information, right? And it gives a very abbreviated version here: test specimens, procedures, and results in accordance with practice E486. So they decided not to put everything about the reporting into this ASTM standard. They made a separate ASTM standard for that. So that's the one that I'm going to show you next. And it says standard practice for presentation of constant amplitude fatigue test results for metallic materials. So once you do the test, Then you come over here and you say, okay, how much information do I have to include when I am presenting the results? Okay, and so this is a document in and to itself. It says this practice covers the desirable and minimum information to be communicated between the originator and the user of the data. From constant force, amplitude, axial, bending, or torsion fatigue test of metallic material. So multiple other standards point to this one as how to present the results. And this I thought was very funny. So this is, we sort of make jokes about this when we're studying engineering, but it says the values stated in either SI units or inch-pound units are to be regarded separately as standard. The values stated in each system are not necessarily exact equivalents. Therefore, to ensure conformance with the standard, each system shall be used independently of the other, and values from the two systems shall not be combined, right? So this can be especially tricky if you're working with maybe a multinational company. Some people use SI, other people use English units. That's what we have in the United States, and so always use the same units throughout. Don't mix units. Even if you're converting correctly, don't mix units. Okay. So how should these fatigue test results be presented? The first thing it says is give a table, right? It says tabular presentation, okay? So basically just provide all the data first, right, in a table form where everything is on there. So if anybody wants to know exactly what the stress was out to X number of digits or exactly how many cycles it was to failure, they don't have to go on the plot like we're doing in this class and like sort of try to estimate it, right? They have the table, they have the data. So it should include specimen identification, whatever was stamped on the end, test sequence, that means chronological order of testing. That could be potentially many repeats in a row, or if you have different conditions that you're applying in a research context, then you may want to randomize the situations such that you don't have systematic error from the way the order that you're doing the tests. Dynamic stresses, and they are very specific. They say any two of the following: maximum, minimum, mean, amplitude or range, and stress ratio, right? So you have to provide at least a couple of numbers so people can understand the stresses being applied. Fatigue life or cycles to end of test. Cause of test termination. Did you turn it off, or did it turn off by itself because it never failed? And end results of post-test examination when applicable. So that means, did you take it over to the microscope and look at it, and what did you see, right? X dimension of crack, grains, plastic zone, whatever you saw in the microscope, you note it. If test frequency varies from specimen to specimen, it shall also be included in the tabular presentation. If more than one machine was used, right? So let's say there's a lab that does a lot of this. They've got 10 load frames, right? But one of the load frames had to go back for repair, so they got a temporary one. It's a different kind, whatever. You have to consider those kind of things. And it says you should sort of specify machine identification. Was it tested on frame 2, frame 8, frame 6? So if somebody wants to go back and look for systematic errors in that, they can. Okay, here's just an example of a table, right? We've all seen tables before. And so this is just a visual representation of what was in that paragraph there. And then this is the part I really want to focus on for presenting the data, right? It's the SN diagram, okay? So I'm going to read this one and then we'll look at the one that's provided. So it says a common graphical presentation is the stress life diagram. The dependent variable, fatigue life, N in cycles, is plotted on the abscissa, a logarithmic scale. So it tells you exactly the scale, what axis it goes on. The independent variable, maximum stress, S max, stress range, or stress amplitude, you can choose. And then you choose a unit, PSI, KSI, millinewton per meter squared, or megapascal, is plotted on the ordinate, an arithmetic or logarithmic scale. So you can do linear or log on the y-axis. It's also acceptable to plot the independent variable on the abscissa and the dependent variable on the ordinate. They give an example of that, but I'm not going to show it. Statistical analysis of the data may be used to fit a line, linear or curvilinear, to the fatigue data. A description of the analyses used should be presented. For example, if the data are fit by regression, the equation and measures of dispersion, like that R-squared value and stuff, should be included in the presentation. And note 3 here is pretty important, and I know it's quite small for those of you in person. The above described procedure develops the SN diagram for 50% survival when the logarithms of the lives are described by a normal distribution. However, similar procedures may be used to develop SN diagrams for probabilities of survival other than 50%, right? So that goes back to, I think it's chapter, I don't remember what chapter it is in the book. It's the introduction to fatigue, maybe chapter 7, where they talk about the different reliabilities, right, of these SN diagrams. So here's what they provide as an example of like a really good SN diagram that has everything on it. So the first thing you'll notice is that it has data, and it has many, or a decent number of replicates at each stress level. This is a constant stress test that we're doing. So this test was done at 50 KSI, 47 it looks like, 43 or 44, and then some values below that as well. And at the highest stress values, the data is pretty tight, right? Doesn't have a lot of variability in its fatigue life. But if you came down here and look at it, it's kind of here to here, right? And so if this is 10 to the 5, and here you go, 9, 8, 7, 6, 5, 4, 3, this would be kind of 2 times 10 to the 4, I think is where it starts here, right? There's a decent distribution in there. But by the time we get out to 10 to the 6 cycles and those lower stresses between about 40, let's say 37 and 42 KSI, the data starts to have a much bigger spread in it, right? And that's where we start to define something like an endurance limit for this material, because there were multiple tests that were beyond the definition of how many cycles we were going to go on this test, right? So if you go out to, let's say this is 1 million, so 2, 3, more than 3 million cycles here, and you're at 100 hertz in the lab, right? You can calculate how long that's going to take. And so it's going to take a very long time. And so we have to cut it off at some point, right? Maybe 5 times 10 to the 6, or maybe 10 to the 7 here, and list how many specimens did not fail, right? And so that from that, you could sort of define like a fatigue limit here. This ASTM spec does not give you any procedures for here's how you define the fatigue limit. And so unfortunately, this is more for this sloped section than it is for the endurance limit. But here's everything that they tell us, right? And so they provided an equation here, right? What are the numbers of that line that was fit? And for a regression analysis, what is the R-squared value, right? How well does that line fit to all the data? So in this case, not including all of the ones that went higher than the number of cycles maximum that we prescribed, the goodness of fit here, R squared equals 0.9238. Okay, so it's not terrible. And then up here, they list the test conditions. What's the material? Ground surfaces. What was the frequency of test? It says 26.7 hertz. It says R equals 0 here. Oops, come on, pen. So for R equals 0, we can go back, if we remember kind of our stress amplitude equations. I also put it here on the bottom right. That is a ratio of the minimum load to the maximum load, or minimum stress to maximum stress. And so if R equals 0, that means it's an axial load and then back to 0. And then an axial load and then back to 0. It has an ultimate tensile strength of 63 KSI, and tests performed in air at room temperature. It gives you a little key if you didn't figure out what the black data is versus the open circle data. And it tells us exactly what's shown on each axis. So it says fatigue life N in cycles. And it doesn't tell us what the failure criteria is on here, but that should be included, I guess, in some sort of information that's provided along with this plot. And then this tells us that it is the maximum stress in KSI. So this is not a fully reversing test where we are provided the amplitude on the y-axis. This is a axial and release type test where R equals 0, and then we are given the maximum stress on the y-axis. So if you're going to say apply this using some other concept that you learned in this class, make sure that this is the type of diagram that can be used to do that. If it's not, then you either need to do an analysis that matches the diagram or come up with an equivalent stress that matches kind of what is plotted here, right? So we do that when we talked about the Goodman criterion for non-zero mean stresses. We said all our SN diagrams have a zero mean stress. So we have to get an equivalent stress that we can then basically use that plot or use that data to do our design or to see if this thing is going to last. And here, you may actually have to do some kind of inverse, right? As long as you know what you're doing or you're following a procedure, let's say laid out in ASTM standard, then you're using the plot correctly. Okay. So this is kind of the main feature of the report that would come out, right? Is this fitting? And then I wanted to mention one other standard because we are going to start looking after this. We're going to go back to the textbook and we're going to start thinking about some other effects like stress concentrations. And we're going to talk about low cycle fatigue. So low cycle fatigue is the part of the plot that we've kind of done a lot of hand waving on. And it's this part of the plot up here, right? Where we're at low cycle fatigue, so less than 10 to the 3, 10 to the 4 cycles. And we just say sort of, you know, if stay in the high cycle fatigue range, then you have stable crack propagation, you have an endurance limit, right? These things we're very comfortable with. Don't go there. But some applications require design for low cycle fatigue, right? So applications where there would be less than 1,000 operational cycles, applications that are very specific or that experience extreme conditions, right? So pressure vessels that hold nuclear material or something like this, right? We don't have magical materials that we just sort of like mine out of the earth and use for those applications. We have to use the best materials that we have available. And so we also have to understand how those materials that we have operate in low cycle fatigue conditions. And so there is a test method for something that's more appropriate for low cycle fatigue, which is a constant strain or strain-controlled fatigue testing. So the prior one was stress-controlled fatigue testing, which aligns with our stress life approaches for high cycle fatigue. This one is strain-controlled, and that's going to align a little bit more with how we consider low cycle fatigue. And so this is the test method, right? So this doesn't tell us necessarily how to interpret the results, but this standard is quite long compared to the other one because it actually gives us a nice theoretical basis for things that make it into textbooks, like the one for our class. So it says this test method is applicable to temperatures and strain rates for which the magnitudes of time-dependent inelastic strains are on the same order or less than the magnitudes of time-independent inelastic strains. So it gives this very technical definition of scope at the beginning, okay? And so it's basically saying that there's two types of strains that are not elastic, okay? Some of them are time-dependent, right? So we have our elastic strains, sorry, why did I write P? Elastic strains that we're very familiar with. They follow Hooke's law, we like that. And in this standard, they're going to talk about two types of inelastic strains. So one is going to be, say, inelastic, IN, and it's going to be time dependent. So this is something we haven't yet covered in the class, but we will talk about, which is creep behavior, right? So if we have creep, everything is time dependent, right? Because creep is related to things like time and temperature. And then we also have a strain, which is inelastic, which is time independent. So it basically is plastic deformation, right? A load-induced or temperature-induced change that really is not due to duration, okay? And so I know we're sort of out of time for today, but I'll end on this slide here. So this shows you a plot, and we'll be looking at a lot of these plots. This is stress and strain. If you start at 1, then you load a sample up, and then you let it stay at the same strain, but the stress relaxes, and then you unload the thing, right? So we'll now have to deal with dwell times and time-dependent behaviors interspersed with time-independent behaviors like elasticity. And so we'll talk a little bit about that in the coming weeks, all right? Please post on the discussion board questions you have about the exam, problem set 4, or things that I've said today. And there'll be a lot of stuff going on Canvas in the coming days. So I will probably see you there. I'll also see you back here on Thursday for another lecture. All right, thank you.